Hello everyone, this is Group 1 and we are doing the analysis of Methanol-Water binary phase system. Binary phase diagram is a graphical representation of two components like methanol and water. It is divided by line forming regions of solid, liquid and gas. And by studying this diagram, we can identify at which point or area where different phases exist in equilibrium. Methanol is widely used in the production of various chemicals which highly benefit the pharmaceutical, textiles, and plastic industries. And for your information, methanol is potentially replacing our fossil fuels because it is densely packed with high energy. And how do we produce methanol? We produce methanol by converting carbon dioxide, and with further purification process by integrating dual catalyst system, which increase the efficiency of clean fuel production by 66%, which lowering the carbon footprint. Our objective is to analyze the methanol-water binary phase diagram and then to quantify the distribution of phases in equilibrium using laboral analysis. Last but not least, to justify how does the application of this system support SDG 12, which is responsible consumption and production.
Hi, my name is Ignatia Irmina Joshua and my metric number is 113102. I will present my part, which is Task 1, Selection and Analysis of Chemical Component. First of all, why we choose methanol-water binary system? This is because it is commonly used in industry where methanol-water binary system is widely used in chemical engineering, especially in industrial separation and purification processes, with distillation being most common application. Next, to understanding for vapor-liquid equilibrium, VLE, is very important. This is because knowing the vapor-liquid equilibrium between methanol and water can help engineer separate methanol efficiency by understanding how the temperature and composition affect phase change. Besides that, the experimental data can help design distillation column, where it can use to choose important design parameters such as reflux ratio, number of stage, and operating pressure in distillation column. Furthermore, it can use in process control and advanced separation method, where this methanol-water binary system is studied in process control to keep separation stable and used in advanced methods like per-evaporation membranes to improve the energy efficiency. Last but not least, it is important for the thermodynamic modeling and simulation. This is because methanol and water show non-ideal behavior, which is this system is often used to test and validate thermodynamic models and process simulation software such as Aspen Plus. Move to the next slide, which is discussion for phase diagram given. For identifications of component, the component that we use in this binary system is methanol and water. Methanol is a component more volatile, while water is less volatile. Therefore, methanol will vaporize more easily than water because equilibrium methanol will be enriched at vapor phase. Next is types of phase and phase field. The phase diagram given is TX5 phase diagram at 180 m, which is represent the vapor-liquid equilibrium behavior of the system. There were three phase diagram, which is single liquid phase, were located below the bubble point curve that represents in green curve. For two phase, which is vapor-liquid equilibrium, that located between the bubble point and dew point curve that represents in red arrow label, and lastly, for single vapor phase is located at above the dew point curve, which is represent in blue curve. For tie line, it is the VLE region, where it is shown that liquid and vapor phase coexist at the same temperature but different composition. Lastly, influence of temperature and pressure on composition. The temperature strongly affect phase behavior at constant pressure, which is at 180 m. For instance, at around 82 degrees Celsius, A liquid composition of X water equals to 0.19 is in equilibrium with a vapor composition of Y water equals to 0.58. This is showing that the vapor phase is richer in methanol. For pressure, it is also can be influence equilibrium. For example, if the pressure are decreased, the lower boiling temperature can change equilibrium composition, while if the pressure is increased, it can shift both bubble and dew point curve to higher temperature, requiring more energy for phase change.
Hello everyone, my name is Theodore Bongyik with matrix number 108561. Today I will be presenting the Group 1 Methanol-Water binary phase system analysis for my section of Task 2, Level Rule Analysis. To begin with, assumptions must be made before level rule analysis can be performed. First, overall composition of the methanol-water mixture should be at 35% methanol. Second, the pressure of the mixture should be at 1 atm. Third, temperatures of the mixture should be at 67 Celsius, 82 Celsius, and 92 Celsius. In order for level rule analysis to occur, temperature composition phase diagram for methanol-water mixtures at 1 atm with additional guides for level rule analysis is provided in the following slide. Based on the diagram, at temperature of 67 Celsius, only liquid is present within the mixture. This indicates that the weight fraction of the liquid phase is 100% of weight. Furthermore, at temperature of 92 Celsius, only vapor phase is present within the mixture. This shows that the weight fraction of vapor phase is 100% by weight. However, at temperature of 82 Celsius, both liquid and vapor phases are present within the mixture. The weight fraction of liquid phase is 59% by weight, whereas the weight fraction of vapor phase is 41% by weight. These values of weight fractions of liquid and vapor phases are determined through the level rule calculations as shown in the following slide. Based on the level rule analysis, it is found that at temperature of 67 Celsius, the mixture has 100% by weight of liquid phase. This means that the mixture has exclusively liquid phase within itself. This is due to the fact that the temperature of the mixture is below the bubble point. This shows that the temperature composition point is in the liquid phase field. Furthermore, at temperature of 92 Celsius, the mixture has 100% by weight of vapor phase. This means that the mixture consists exclusively of the vapor phase. This is due to the fact that temperature of the mixture is above the dew point, which consequently indicates that the temperature composition point is in the vapor phase field. However, at temperature of 82 Celsius, it is found that the mixture has 59% weight of liquid phase and 41% of weight of vapor phase. This indicates that both liquid and vapor phases exist within the mixture. This is due to the fact that temperature of the mixture is between bubble point and dew point. This shows the presence of vapor-liquid equilibrium as the temperature composition point is in the liquid plus vapor phase field. Essentially, the amount of liquid phase decreases as temperature increases starting from bubble point to dew point. Furthermore, the amount of vapor phase increases as temperature increases starting from bubble point to dew point. That is all for my section of the Group 1 presentation. Thank you for your time.
Hello there, my name is Muhammad Ali Ashraf bin Jahidin. My matrix number is 110911. And in this video presentation, I would like to talk about our task 3, which is SDG evaluation, and the overall conclusion for our topics, which is methanol-water binary systems. So according to the UN or United Nations, SDG 12 shows that the ensure of sustainable consumption and production patterns of that specific product. So in this case is methanol-water. So how does it relate to the SDG 12 with our topics methanol-water binary systems? Well, industry can recover and reuse methanol instead of discarding it as a waste. This supports SDG 12 by promoting recycling, reducing hazardous waste and generations, and encouraging sustainable chemical management. Other than that, when methanol is produced from renewable sources, such as biomass or capturing carbon dioxide, and efficient management in water-based systems, this further aligns with SDG 12, where it reduces the dependence on fossil fuels and lowering it the environmental impact. So we're moving on to the final part, which is the overall conclusion. So methanol-water binary system represents a huge fundamental and highly significant mixture in a chemical and chemistry industry or engineering, with wide-range industrial, environmental, and scientific importance. The complete miscibility of methanol-water and its strong intermolecular interactions result in a non-ideal behavior that directly influences the key thermodynamics properties, such as entropy, enthalpy, Gibbs energy, energy balance, and etc. This plays a huge role in understanding the behavior of the methanol-water. It may sound simple, but it's a very, very extraordinary complex materials. And also, the understanding of methanol-water binary system also enhances the chemical safety and environmental protection based on the SDG 12 that we talked about earlier, where it promotes an alternate fuel rather than using fossil fuels or coal and etc. And also, instead of discarding it, we can use just recycling it as a fuel that we talked about earlier. So it also promotes SDG 12 a lot in the chemical industry.